Let's start again. I'm Carolyn Winther, and I'm the director of the Stanford Humanities Center. And it's my great honor to welcome you to the 2018 Presidential Lecture in the Humanities and the Arts. This series brings the most distinguished scholars, artists, and critics of our time to the Stanford campus for lectures, seminars, panel discussions, and a variety of related interactions with faculty, students, and the community at large. Funded by the President's Office and administered by the Stanford Humanities Center, these programs explore the most important and compelling ideas in the humanities and arts in the 21st century. It's my great honor tonight to introduce the president of Stanford University, Mark Tessier-Lavigne, who will then introduce our speaker for the evening, Siddhartha Mukherjee. After Professor Mukherjee's talk, there will be a brief opportunity for Q&A. Since becoming president of Stanford University in 2016, Mark Tessier-Lavigne has been an advocate of the importance of the humanities and arts as disciplines that open our minds and teach us how to think about the great questions facing humanity in the past and in the present. So we're very pleased that he could not only join us this evening for the presidential lecture, but that he enthusiastically agreed to introduce our honored speaker for the evening, who is someone like the president, who embodies the happy intersections between a life dedicated to science and a commitment to the humanities. Please join me in welcoming President Mark Tessier-Lavigne.
Great. Well, thank you so much, Carolyn, and thank you all for being here this evening. It really is a very special pleasure for me to introduce tonight's speaker, Dr. Siddhartha Mukherjee. That's because Sid is not only a practicing physician, a pioneering scientist, and a best-selling author, he's also a close personal friend. Sid is a veritable Renaissance man. He's an accomplished physician-scientist who's done groundbreaking work in the biology of blood development with a focus on understanding malignant and pre-malignant blood diseases. He's also a master storyteller who's made the scientific explorations around cancer and genetics come alive for millions of readers around the world. Sid is the author of The Emperor of All Maladies, A Biography of Cancer, which won the 2011 Pulitzer Prize in General Nonfiction, and which was later made into a 3-part documentary by Ken Burns. The book tells the story of cancer itself and past and present attempts to control it and to eradicate it. Now, I'm not a book reviewer, but I can assure you that if you haven't read this book, it is a must-read, a real page-turner. It's beautifully written, compelling in narrative, completely accessible to non-scientists, and yet, as I can attest to as a scientist, both sophisticated and fully accurate in its scientific presentation. It really is a true tour de force. And the same is true of his most recent book, The Gene, An Intimate History. This book provides a sweeping history of our understanding of inheritance and of genetics, from Aristotle through Mendel to the present day. It also draws on Sid's personal experiences of psychiatric illness in his family to explore the influences of our genomes and the limits of those influences on our daily lives. The book has been a New York Times bestseller and was one of the Washington Post's 10 best books of 2016. Now, we're especially proud of Sid because he is one of our own, a graduate of Stanford University. From here, he went to Oxford as a Rhodes Scholar and then to Harvard Medical School. Today, he is an assistant professor of medicine and staff cancer physician at Columbia University Medical Center in New York, where he continues to see patients, in addition to performing research and, of course, to writing about science. It's also in New York that my wife Mary and I, when we were living there, had the pleasure 6 or 7 years ago of meeting Sid and his wife Sarah Z, the renowned artist and MacArthur Genius Award winner, who will be giving the Wilsey Lecture tomorrow at 6 p.m. here in this very room, so please be here again tomorrow. We'll see you then. The four of us became good friends, and I can assure you that there's no greater joy than spending time with Sid and Sarah, whether to discuss science or art or politics or just life in general. to go to a Michelangelo or a David Hockney exhibit, or to play touch football together with some youngsters, and to survive to tell the tale. Sid's topic tonight is Notes from the Edge of an Experiment, or Cancer's Anxieties. Please join me in welcoming back to Stanford, Dr. Siddhartha Mukherjee.
So I cannot tell you what an honor it is to be back, and what a pleasure it is to be back at Stanford. And thank you for inviting me to this lecture. I thought I would begin with the central argument. So in the late half of the 20th century and in the early part of the 21st century, two very striking developments occurred in our understanding and imagination of cancer. You might think of these two developments as developments in time and in space. The first was that the locus of cancer as a disease, formerly somewhat unknown and mysterious, that locus moved from the exterior to the interior, from the outside to the inside, and from the non-self to the self. In other words, we became progressively aware that the locus where cancer develops, or the cause of cancer, cancer arises from mutations in genes that are fundamental to the development of human beings, human cells, to the physiology of our cells, to the metabolism of our cells. That for most part, cancer was a disease in which the corruption or the distortion was fundamentally a distortion of self. In the early part of the 21st century, there was also similarly a movement in time in which our understanding of the locus of cancer moved from people who have, men and women and children who have the disease, who are carrying the disease, the burden of disease, to men and women before they have the disease. Emblematic of this movement was the word previvor, which is a word that has now become part of the language of cancer. And that word refers to the idea a previvor is someone who has yet to develop cancer, but is a survivor of that future development of cancer. It's an Orwellian word, and people have a hard time thinking about it. But it's a survivor who has not yet developed the disease that he or she may develop in the future. Think about that for a second. But nonetheless, the idea that in time, we began to think about patients before they became patients, to survey them, to try to understand their biology. Often, we are at a place where we are performing deep surveillance of some of these people. We are annotating them genetically, and we are making them or welcoming them into what Barbara Ehrenreich and others have called cancer land. This movement, these two movements in time and space in cancer, carried with them, and we've seen this, carried with them therapeutic breakthroughs and therapeutic benefits, the capacity to treat in the adjuvant setting or early after the removal of a cancer, when the body is technically cancer-free, using a targeted therapy had a massive impact for certain forms of cancer. And certainly the capacity to genetically annotate those at risk for cancer using genetic tools such as the BRCA1 and BRCA2 genes allowed us to survey people, men and women, before they could develop the disease. The capacity to locate in space the disease in the interior of the self obviously had a majestic influence on our understanding of cancer and reformulated how we think and treat cancer. There is little doubt that this science will continue into the future. But my talk today as a humanist is to consider what this does to our imagination of ourselves and to the imagination of cancer in the future. What does it do to us as a culture when the locus of disease moves from the exterior to the interior? What does it do as we move the locus of disease from people who are survivors to people who are previvors? And that's going to be the bulk of what I'm going to talk about. I'm going to begin with comments that were written in 2010 in a review of The Emperor of All Maladies in The New Yorker by Stephen Chapin, the historian, And Chapin wrote that a world in which cancer is normalized as a manageable chronic condition would be a wonderful thing. And in fact, this is in some way an underestimation of how wonderful it would be, because of course we would have the capacity to bring tools to the problem that we didn't have before. But a risk factor world in which we think of all of ourselves as precancerous would not. He continued, it might decrease the incidence of some forms of malignancy while hugely increasing the numbers of healthy people under medical treatment. And he concluded that would be a strange victory indeed, in which the price to be paid for checking the spread of cancer through the body is its uncontrolled spread through the culture. That is an idea that I want to explore more deeply. What is it to check the spread of cancer in the body? What does it do to the so-called, as Chapin put it, the uncontrolled spread through our culture? And I was reminded in writing this talk of work done in an earlier decade by the sociologist Erving Goffman, who wrote about the idea of a total institution. A total institution, Goffman wrote, is a place of work and residence with a great number of similarly situated people cut off from a wider community for a considerable time, together lead an enclosed, formally administered, and I would add, surveyed round of life. And one of the things that I want to consider with you today is whether we are at the risk of creating cancer as a total institution, and what that does to us or our understanding of ourselves as humans. And in order to do this, I thought I would introduce two clips from the film that I made with Ken Burns. I've chosen these two clips for very specific reasons. The first one we called while the clip was being edited, and I changed the title of the talk somewhat. I'll come back to the notes from the edge of the experiment. But the first one, when we were cutting on the floor, we used to call Welcome to Cancer Land, or Laurie Wilson's haircut. Laurie Wilson is a breast cancer surgeon, was a breast cancer surgeon originally she trained at part of the Hopkins program, then had an incredibly successful, she was a professor, has an incredibly successful practice in breast cancer surgery. Actually, while, this is a strange but true story, while we were filming The Emperor of All Maladies, found that she had bilateral breast cancer. And the first clip is from Dr. Laurie Wilson's welcoming into Cancer Land. The second is a very different kind of clip, but of course goes back to the idea of cancer being located in the interior. This is an interview with Harold Varmus and Mike Bishop, and their discovery of the startling discovery in the 1970s that the genes that in their mutated form cause cancer are actually genes that are already present in all human cells, and those genes are a substrate that are ultimately become cancerous once they are mutated through a variety of insults. You obviously will already understand why these two clips are together. One of them begins to describe what it is like, the experience, the human experience of welcoming into Cancer Land, and the totality of that experience. And the second one, again, asks the question of what it is like to realize that the locus of illness in cancer, this disease that was and is continuing to progressively envelop our culture, when the locus of that disease moves from the exterior to the interior, what that moment of discovery was like. So I'll show these two clips, they'll go back to back, and I'll come back and continue this conversation of these two movements and what they have done in history and how they influence our understanding of cancer today. So if you can dull these lights and then show the clips, thank you.
At least he tasted it.
You're a funny boy. You know that?
Mommy likes cherries.
It's been a month since Laurie's diagnosis, and her 20-week regimen of chemotherapy has begun.
Like some. Yum, 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 yum. I know you!
Oh, my wife, Lori.
Hey, how you doing? Nice to meet you.
Good to meet you. Thank you for coming.
Like the other most. I go first. Yeah.
My husband actually is going to shave his head with me, and so we will, until my hair grows back, we'll both be bald together.
Wow.
He's my rock. He's been there for everything.
He's looking good.
Y'all forget I've been bald-headed before, 20 years ago. Yeah, before Lori and I got together in the first winter when I grew my hair. And then Lori liked my hair when I haven't shaved it since.
Oh, what a story.
That's sweet.
So cute. All right, next. Yeah.
Let's see.
You can take it all.
Oh, okay.
Be okay.
It'll be okay. I don't buy into the why me because so much of cancer is not predictable, is not set on family history or any feature, and so absolutely could be me.
Hey, Nene.
You recognize mommy?
Oh.
I have a 19-month-old and so absolutely could be me.
Hey, Nene.
You recognize mommy?
Oh.
I have a 19-month-old and
This virus that causes cancer has 4 genes, and they find that a closely related virus that doesn't cause cancer has 3 genes. And that's a very interesting difference. What's this extra gene? And then the evidence begins to mount. This gene, right, carried by the virus, the extra gene, can cause the cancer. It was called an oncogene, a cancer-causing gene in the virus.
And then we began to think about a puzzle, and the puzzle was, why does the virus have this cancer gene? This gene we called SARC, the only thing it does is to convert the cell to a cancerous state. So the cancer gene seemed almost superfluous.
Well, if the virus doesn't actually need the gene, why does it have it? Where'd it come from? Maybe they thought the cancer-causing gene did not originate in the virus at all. Maybe it originated in the chicken.
To my astonishment, when we looked in normal chicken cells, we found something that resembled the SARC cancer gene in Rous sarcomavirus. It was a riveting moment.
Everybody expected that the SARC gene, the SARC oncogene, the cancer gene, was a natural resident within the genome of Rous sarcomavirus. But in fact, the profound discovery they made was that Rous sarcomavirus had actually had kidnapped that gene from the repertoire of normal genes that are normally stored in the genome of a normal chicken cell.
If the SARC oncogene had actually descended from a normal gene in chickens, where else might it be found?
We looked at ducks, we looked at emus and rheas, which are the most primitive birds living, and then eventually, by fiddling with the technology, we could show that it was even in humans.
The fact that SARC existed in all organisms, not just in viruses, but in chicken, in geese, and in humans, that fact gave a very crucial clue, because that meant that genes that are capable of causing cancer are already existing inside animal genomes. I mean, imagine how exciting that would have been. Now, all of a sudden, you begin to see through the darkness a glimpse of what the clear theory of cancer is. There are genes in your body that control normal cellular growth, and if you disrupt these genes, you essentially begin to unleash cancer.
So I want to now trace a little bit of the history of this idea of as I said, the relocation into the body of cancer. When the earliest descriptions of cancer are, of course, hidden away to some extent in human history. There's even no word for it. We believe that the first description of cancer occurs in this Egyptian document called the Edmund Smith Papyrus, where a mass in the breast is described. This comes from around 2500 BC, and a mass in the breast is described as dense and cold as the hemat fruit. There is no name for this disease, and more importantly, the scribe who writes also says that there is no treatment for this disease. And it's not until years later, decades, even centuries later, that we begin to get the word cancer. And what's interesting about it as a metaphor is that the word itself is located outside the body. It's located in the idea of a crab, a foreign organism, that has come to inhabit the body. In this case, people thought that the word karkinos for crab exemplified what it would be like for a crab-like creature to have crawled inside the body, and the engorged blood vessels around a tumor were thought to be the legs of the crab, and hence the idea of the crab and karkinos came apocryphally. People argue that Hippocrates was the first to describe cancer as the crab, but certainly it finds its way to through the literature, and certainly it finds its way through medieval literature and becomes formally described as cancer or karkinos, as the idea of a resident in the body, unnatural, but living under the body like a crab would live under the sand. It's not until much later, again, centuries pass, it's not again until the late half of the 1800s and the early part of the 1900s when we begin to think about cancer as the idea of a betrayal of cells or the betrayal of self. This is Rudolf Virchow, and one of his enormous contributions was to realize that regardless of where cancer originated, liver, brain, breast, and various cancers, that there was a fundamental abnormality that linked all of them. Virchow also coined an extraordinarily important idea in the world of cellular physiology, and that was omnis cellula est cellula, from cells come other cells. And if you think about that idea more thoughtfully, people before Virchow had imagined that cells were born through a process that was unknown. They could come out of the miasma without having a cellular precursor. But if you took Virchow's work seriously, Virchow tracked cells as they moved through the lifespans of embryos. If you took that work seriously, this is in normal physiology, you'd have to say that the only way that cancer could arise was from a normal cell. Something must have happened, if you logically followed that work, something must have happened to a normal human cell to transform it into a cancerous cell. And therefore, the question was briefly raised that what was that something? Was it an exogenous agent? Was it something that was located inside the body? It was described as transformation, but what was the nature of the agent? Virchow himself didn't know. Virchow's work was thought about quite deeply for a while, but the pathophysiology of cancer, why cancer existed, what its cause was really largely forgotten. People argued about whether it was a viral cause, whether it was coming from the outside. However, while this debate was raging through parts of the scientific community, the world of cancer treatment was set on fire by the idea that whatever it was, however it came, however it arose, the removal of this foreign body would be the cure for cancer. This would culminate in the Halsted radical mastectomy, which was really described by Halsted as a method to save women from this malignant thing, this malignant object that had taken over their bodies. And in fact, the only way to cure this malignant object was not just to attack it locally, not just to remove it locally, but to actually extirpate it, as Halsted described it, with the most radical surgery possible. And in fact, there began in the 1890s into the 1910s and 1920s a kind of manic race in the world of surgery to remove more and more tissue, not just the breast, but in fact the underlying lymph nodes, the muscles, and leaving patients, leaving women deeply disfigured. But this was taken as par for the course. This was understood as the necessary implement that had to be deployed in order to remove this, this visitation that had taken over a person's body and ultimately extirpate it and remove it so that the woman would be cured. This is a quote from Halsted. In fact, that etching is from one of Halsted's papers. As Halsted says, the patient was a young woman who I was loath to disfigure, but nonetheless, this disfigurement was considered part and parcel of the attempt to cure cancer. And it really wasn't until the 1970s that we went backwards towards Virchow's description of cancer as arising as a process, a distortion from a normal cell into a cancer cell, a transformation, as was soon described, of a normal human cell into a normal cancer cell. And that, as you saw in the clip, really shook the world of cancer medicine, cancer biology, in fact, human biology, by its very spine, because all of a sudden the locus of disease was moved away from something foreign, something that could be described as far away, into something very much located in the interior. In other words, the very genes that allow us, our cells, to live, divide, metabolize, if you make mutations in those genes, the cells now are unable to stop living, stop dividing, stop metabolizing, and thereby unleashing the malignant process. This was a discovery made widely, and several people entered this. Of course, I showed you a clip with Bob Weinberg and Harold Varmus, but the implications, particularly the cultural implications, the humanistic implications of this idea that cancer was that kind of disease which we hadn't encountered before, where the animus of the disease emerged from the self, was widespread. And it took some time before we began to fully understand the implications for human biology in general, but of course also the implications for how we think about ourselves. The biological implications were just as acute. In fact, the idea that cancer arose as the consequence of mutations in genes that were already resident in the human body solved an age-old problem in cancer biology, which is how could you possibly explain the fact that heredity, environment, chance, and viruses could all cause cancer. These were known for a long time. This is a picture of Hilario de Juvia, who's a Brazilian ophthalmologist who noted that there was a very rare variant of cancer called retinoblastoma, which ran through a Brazilian family with extraordinary penetrance. And the only way, he wrote his paper, it was largely neglected, but the only way you could now make sense of that observation was to think that genes must have a role, or heredity must have a role in cancer. This is Percival Pott, the English surgeon, who separately noticed that environmental influences could cause cancer. Percival Pott realized that chimney sweeps in England had a very, very high incidence of scrotal cancer. And Pott, in fact, coined the term carcinogen, something that generates cancer, and hypothesized that it was something in chimney soot, in chimney dust, that was responsible for cancer. We knew that there was a role of chance in cancer. Many families with familial histories, people, men, women, would develop cancer at different times. We knew that there was a role that chance played from a variety of significant bodies of evidence. And of course, for the longest time, as Varmus and Bishop pointed out, people thought that viruses could also cause cancer. But the unifying theory here was that in all four cases, whether genes, the environment, chance, or viruses, in all four cases, the material that was being tampered with, the material that was changing, mutating, whether it be through a carcinogen, whether you inherited it from your parents, whether it came from a virus, the material that was changing were genes that were already resident within cells. And of course, I did not put this up for humorous reasons. I talked about extensively in the book. The implication of this, particularly in the 1970s and 1980s, results in a kind of moment in which we begin to question and try to understand the body as a series of vulnerabilities which are exposed or manifested when, as a collaboration, for instance, between the environment and the body, somehow that the problem locates itself within the body. They have, as in the Pogo cartoon, we have met the enemy and he is us, or in the beautiful statement read at the end of the Nobel Prize for Varmus and Bishop, in which they described cancer as a distorted version of our normal selves. In the years that followed, much of our science explored the idea of this distortion. What was it like? How many genes were required to transform, going back to Virchow, a normal cell into a cancer cell? How do cells become cancerous? And the idea that emerged from that would eventually propel our understanding of not only cancer, but also our understanding of how to prevent and treat cancer in patients who had not even manifested the disease. I'm now moving slowly into the second half, not the location of cancer, the change of location of cancer in space, but the change of location of cancer in time. This idea came out of work performed in the 1990s and early 2000s as we began to sequence genomes, human genomes, normal human genomes, and was extended as we began to sequence cancer genomes. So here's a schematic of that. We need to understand that impulse. We need to understand that idea. So I've made a schematic of it. I'll come back to the schematic in the talk. But this is, say, a patient with breast cancer or a man with prostate cancer. And by the 1990s, our ability to sequence cancer genomes and compare what mutations had been accumulated in those genomes compared to normal cells began to accelerate. So here, for instance, I've created a schematic in which, if you imagine the entire human genome as a piece of paper, a blank sheet of paper, you could, certainly by the early 2000s, pinpoint the mutations that had accumulated in some cells, cancer cells, that were causal and were responsible for the development of a malignant behavior. What was interesting is that we could now compare between one human being and a second human being, and we found that the patterns were very intriguing in the following manner. Here's a second human being who also has the same cancer. Microscopically, pathologically, they look the same, but in fact, the spectrum of genetic mutations in the second human being, same cancer, breast cancer or prostate cancer, but the spectrum of mutations was different between different individual samples or different individual specimens of cancer. Here's a third example. This brought home the idea, which we had not encountered in the history of illness, which is that every specimen of cancer was its own specimen of cancer, or that every instantiation of the illness was its own instance of the illness. No other disease that we know of in human history had this level of molecular or genetic diversity. We're still struggling to understand, to comprehend and to come to terms with this level of genetic diversity. But one of the things that was animated by the discovery of this level of diversity is that we began to think about ways or mechanisms by which we could classify individuals with cancer based on these genetic fingerprints, as you will, so that if you had one particular fingerprint of cancer, you would be treated with one therapy. If you had a second fingerprint of cancer, you would be treated with a second kind of therapy. And in other words, the genetic fingerprints would guide what therapies you would be treated with. And there were several examples in the early 2000s going into the early part of this century where this form of targeted therapy with a precision component, targeted therapy where you were previously annotated genetically for your cancer genome, began to come alive. This is an example. This is actually a real map of a cancer genome. Again, if you just take all these maps and you were to collapse them and ask the question, how frequent are certain mutations, you would end up with a map that looks like this. One of the great success stories in these was the development of new medical technologies, new medicines that would look at these cancer genomes and then try to develop therapies that were directed at these particular cancer genomes. And not only was this true for single genes, but it began to be true for networks of genes. So you would actually develop networks of genes and use those to predict which patients would benefit or not benefit from cancer therapy. Perhaps the best example, there are many of them now, but perhaps the best example of this is the drug Herceptin, really invented, I would say, in the environs of where we are sitting now. This is Barbara Bradfield. Barbara Bradfield is the first patient who was welcomed into Cancerland by her diagnosis of metastatic breast cancer, and she is actually patient 0 of Herceptin. She was the very first patient to be treated with Herceptin. Remarkably, she actually had the best response in the entire trial, in that original phase trial, to Herceptin. And she had, as I said, diffusely metastatic HER2-positive breast cancer. She's still alive today. So this is about 18 years after her initial therapy with Herceptin. This is actually a photograph that her husband took on my behalf. I called her up, and this is the last photograph in my book, In the Emperor of All Maladies. And this, of course, is data from that pivotal trial. Women with metastatic breast cancer, women who had been discovered with breast cancer in other organs, in other parts of their body, breast cancer in their lung, their bones, and other tissues, treated without Herceptin and with Herceptin. You can very clearly see why this pivotal trial was a landmark success in the use of a new form of therapy, not classical traditional chemotherapy, but a new kind of therapy, this one an antibody that would recognize the cancer cells where the genetic mutation had made them vulnerable to this particular drug. The important thing, of course, there was little doubt that this kind of therapy, the use of targeted therapy, precision therapy, was important in women where the breast cancer had already spread outside the local environment of the breast. But to the great surprise of our community, although some people said that they would have predicted it, but to the great surprise of our cancer community in the 2000s was a trial which asked the question, well, what if we treated with Herceptin women whose disease had actually been removed locally and they had no signs whatsoever of remnant disease, no detectable signs of remnant disease in their bodies. So everyone following the logic of what I'm saying. So this is compares in late intervention. So in other words, a woman who has had metastatic breast cancer like Barbara Bradfield, the use of Herceptin, there's no doubt that that the survival of these women is prolonged. That's a survival curve. But what was really shocking and important in the world of cancer was this trial, which ran in parallel. This is the use of Herceptin in a woman whose breast cancer has been surgically removed, and there is no evidence of disease left in her body. This is to remove or to dispel any remnant tissue, any remnant cancer cells that were left over and were missed by surgery or had already spread outside but were living in a kind of a dormant way that was outside the local therapy. And this was considered a remarkable trial because all of a sudden we had the capacity to treat not only women with cancer, but really we were treating women with no evidence of cancer, with a history of cancer, but with no evidence of cancer. And this led to what I consider the experiment that began in the early 2000s and that we're still living through. The experiment is whether this strategy of early detection, personalization, and targeted therapy or immunological therapy will allow us to really treat men and women with cancer, often even without the cancer being present in the body, at least visibly present in the body. So to detect as early as possible and to deploy cancer therapies at a point of time where, in fact, we may be surveying for cancer but not even have cancer itself. And so we began to imagine cancer then as a disease of what I might call mitigated risk. Rather than focusing on who has cancer, how to treat that person, we began to imagine that there was a kind of funneling of risk in cancer. How do we reduce and identify those at risk? How do we detect the cancer early? How do we identify those that are likely to progress? And then, how do we treat with the most effective, least toxic therapy to maintain a response and a remission? So the clock of cancer, as it were, began to move backwards towards the identification of risk, towards the identification of those who were at risk before, often before the cancer itself had appeared. And you can imagine that these three arenas would funnel an individual, a human being, through a kind of funnel of risk, ultimately resulting in a kind of report card of risk that would be modified as people aged and people moved through what other people, as I said, have described as cancer land. So how are we, what was the mechanism, what are the mechanisms of identifying people at risk? I would suggest that in this world today, we're increasingly becoming comfortable with identifying people at risk using genetics and using chemistry, and I'll talk a little bit about that. The important thing, of course, in both cases, using genetics and using chemistry, and just to emphasize the point, is that often our goal is to identify and detect men and women at risk of cancer who don't have cancer itself, at least in the old description or in the visible form that we used to use as criteria for treatment. So let's talk a little bit. These are two separate arenas. So let's talk a little bit about this kind of annotation of risk. One annotation of risk, of course, is genetic. Who carries genes, which individuals carry genes where their risk is increased for a particular form of cancer? Are those people, are those individuals, should we be surveying them more actively? If we find incipient cancers in those individuals, should we be treating them, or should we be asking the question, what if those incipient cancers are unlikely to grow because of other reasons? How do we discriminate between those likely to get cancer? How do we discriminate between those and the individuals who are unlikely to get cancer? So our models for this were relatively simple. We had found by the early 2000s single genetic variations, single genetic mutations inherited. So these were inherited mutations which would increase your risk of cancer, the classic one being BRCA1 and BRCA2. So these are mutations that are variations you would inherit from your parents. There were occasional spontaneous mutations, but largely inherit from your parents, where we could detect those mutations based on your family history and use that to survey men and women with BRCA1 and BRCA2 mutations more intensively, therefore, as I said, welcoming them into this funnel-like system in which their risk would be annotated and we would survey them for the development of cancer. But we also knew that if you just take a disease like breast cancer, about 70% of women who have risk based on their family history, so we know there's a familial component to their cancer, 70% of those women did not end up having it, probably the number is even higher, do not have BRCA1 and BRCA2 mutations. So what was this mysterious other 70% where there was an inherited risk, where there was heritable risk because we could see the disease moving through families, and we began to use the somewhat paralyzing description of the syndrome as BRCA3. They were not BRCA1 and BRCA2. We did not know what they were, what the genetic risk was. And so we began to use, but it was a very unsatisfying description because we would tell patients, we clearly know that there's a heritable risk. We know there's a genetic risk. We cannot tell you. And worse still, we cannot tell your daughters if they have the risk or they don't have the risk, or your sons if they have the risk or they don't have the risk, although we know that it's running through your family. So this is the typical kind of BRCA pedigree, the BRCA1, BRCA2 pedigree, where you can see this simple risk. But BRCA3, this more diffuse heritable risk, seemed like something much more complex, like the genetics of things like human height, where you know there's a heritable component. We've known forever. Tall people, tall parents tend to produce taller children. Shorter parents tend to produce shorter children. We knew for a long time there was a strong heritability, but for a single individual, we had no idea what genes were responsible, and we had no idea how to annotate those genes. What has happened in the last 10 odd years is that this complex, the complexity of this kind of risk is now being broken apart, mostly by computational sciences and mostly by a combination of simple algorithms, extraordinarily complex for humans, but simple computational algorithms which are additive, versus more deep learning strategies which go into the genome or can go into the genome and understand complex genetics. I'll give you one example of this from height, and then give you a more, I think, more clinically relevant example from cancer. This is a study that was recently performed, which tries to use deep learning to predict human height. And essentially, it has, if you can imagine, it's a very simplistic description, but essentially takes, on one hand, hundreds of thousands of individual genomes. Again, it's a somewhat simplistic description, hundreds of thousands of individual genomes, each of which where we know the height of the individual. And it asks a computational algorithm, in this case a deep learning-like algorithm, to go into that database and try to attach connection strengths to each of the genetic variations in these hundreds of thousands of individuals and ask, can you predict height based on this? Can you learn to predict height? And this is a curve that shows the data. On one hand, on the x-axis is the predicted height, on the y-axis is the actual height. And what you realize, to me actually, perhaps chillingly, that in fact the algorithm does very well. So if you have an individual sitting right here, over here, their predicted height is about half a centimeter away from the actual height. I'm sure I don't need to convince this audience why this is both chilling and surprising. In other words, you could, if this algorithm worked now on a larger scale, you could predict your child or your unborn child's height, future height, based on genetic information alone. And of course, that has massive implications, not for height, but for a variety of other traits, features, diseases, etc. What's interesting about this is that about 3,000 to 5,000 genetic variations were involved, probably even more. And in fact, the more you do, the deeper you dive in this situation, simplistically speaking, the more information, the more accurate you can get, and the more data there is, the more accurate you can get. This is the second case that I talked about. This is cardiovascular disease, but what's interesting in the chart below is breast cancer. And what you can see again, this, unlike the first case, does not require deep learning. This has been called a polygenic risk score. You can understand why now. Polygenic because multiple genes are involved. Risk score because you're predicting risk. The genetic architecture remains extremely complicated, but focus for a second on these two arrows. The one above is for breast cancer. The one below is for severe obesity. With algorithms like this, in this case, the odds ratio, which is a way of saying the heightening of risk for the particular trait, is about 4.43. In the case of severe obesity, at the top 0.25% of the distribution, the odds ratio is almost 7-fold. So you can begin to understand how we are creating a way of genetically annotating risk before risk occurs itself. And that, of course, has contributed to this idea of previvorship. In other words, all of us right now could begin to be annotated in risk and could begin to imagine ourselves as loci of diseases waiting to happen. Obesity waiting to happen, cardiovascular disease waiting to happen, breast cancer waiting to happen. While this genetic-based assessment of risk is ongoing, we're also simultaneously learning to assess risk through chemical means, really through DNA, and through visual means. This is work actually done at Stanford, but I wanted to illustrate it with a close friend of mine, Will Kiersky, who sadly died last month of metastatic melanoma. This is a picture of Will Kiersky long before he developed the melanoma. His mother went back and found these pictures from, this is at a wedding, and sure enough, there is a lesion that is present. In fact, there are two lesions that are present, one just under his ear and one just on the side of his cheek. Both were malignant. In fact, one was a metastasis of the other. And this would ultimately spread and sadly kill Will Kiersky. Work done recently at Stanford allows us to begin to diagnose and discriminate between these benign and malignant lesions at first presentation based on algorithms. So an algorithm visualizes and asks and learns, much like an algorithm had visualized and learned how to diagnose genetic risk. In this case, it's using a visual cue to distinguish between melanomas that are malignant versus other skin lesions that are benign. And by the way, I've seen, as you can imagine, plenty of melanoma in my life. I could not tell you why on earth this lesion was learned by the computer to be classified as malignant. It looks very benign to me, whereas this lesion up on top, this corner lesion over here, was classified as benign. They actually turned out to be correctly classified, but in fact was learned by the algorithm. And I was reminded when I was speaking to a dermatologist about this study, this came out of Stanford, as I said, I was reminded when I spoke to a dermatologist is that when she is training a new dermatologist, the new young dermatologist, the dermatopathologist, starts with a case study of 0 and goes to a case study of 1 at the first time she sees or he sees a melanoma. The computer, the algorithm, starts with a case study of 500,000. And when you put the new one, goes to a case study of 500,001, and so forth. So the idea that came out of this study, which we discussed at this meeting with the dermatologist, actually wrote about, is an idea which is, again, simultaneously surprising and chilling. What if you voluntarily agreed to send a photograph of someone like Will Kiersky before they were aware of their disease on social media, on Facebook? What if the algorithm could scan through and pick out people who were likely or unlikely to develop malignant disease? Is that a world that we want to live in which we submit ourselves to this kind of surveillance? If that sounds fantastical to you, here is another invention coming out of Stanford itself. This is a fantastical idea of using a perpetually scanning bathtub that would look using ultrasound to see if you had changes in pancreatic anatomy, in ovarian anatomy, things that are occult in the world of cancer. And again, you would voluntarily enter this kind of surveillance as a mechanism to detect this disease in its earliest form. We have no evidence that this will work, and I've repeatedly pointed out that what we do know is that there are patients who will have these lesions who may not end up having cancer for a variety of reasons. We know this from a huge literature where surveillance has been used. But these are more and more sophisticated versions of surveillance, and you can imagine that the body under surveillance is a body where you will detect not only incidental cancers, but real cancers. In the case of Will Kiersky, in fact, we went back and looked at that, and sure enough, the algorithm would have classified that as a malignant tumor. And the final piece of this kind of surveillance is a project that actually we are involved in, but has many, many components. But that is to look within blood itself for the bits of DNA shed by cancer cells long before cancer becomes visible. This is project, one of the companies is actually located down the street from you, called GRAIL. The name itself should suggest to us the ambition of being able to detect, like the Holy Grail, the earliest signs of cancer before cancer appears. This one is an NIH-funded project out of Hopkins called CancerSeek. S-E-E-K is a clever way of also spelling S-E-Q, sequencing, which is a mechanism to look for the earliest signs of cancer in your blood before the cancer actually develops. And they have very impressive early data which shows that, for instance, in patients who have ovarian cancer, this is just mostly retrospective data, but in patients who have ovarian cancer, their capacity to detect this cancer using a blood test goes to 100%. So in other words, every woman who had ovarian cancer was found to have an abnormal signal within the blood without looking for anything, any pathology in the ovary. In liver cancers, it approaches 100%. In breast cancer, less so, and we don't know why. What we also don't know, of course, is what to do with these men and women who've been screened and found to have cancerous predisposition, either through genetic means or through chemical or DNA-based means. What should they be treated? Should we go back to the experiment where we had deployed, like with Barbara Bradfield, targeted precision therapies based on their genetic predispositions? Once you're under surveillance, what happens to you? Do some of these cancers never grow because of seed and soil reasons? Do some of these cancers never take root because the body rejects them immunologically, but they're still detectable by DNA? These are questions that are central to what's going on. And so our idea of how to imagine cancer is under flux. It is itself, to sadly pull the old metaphor, the idea itself is metastasizing. We're changing the way we imagine our imagination of cancer. And that has consequences because we are now repeatedly finding ourselves as human beings under surveillance. So if you think again of cancer in society as a disease of mitigated risk, the questions have now turned to questions like who is likely to progress once you've identified these individuals as people who have or will have cancer in their bodies. I'll spend the last few slides talking about talking about therapies as cancer has moved. As I pointed out, from the exterior to the interior, we're increasingly also using the interior as therapy against cancer. Virtually all of you've heard about immunological therapy for cancer. This is one of the startling developments of really the last decade or so. And the idea that we are trying to understand not cancer in isolation, but cancer in its presence within an immune system, to the capacity to raise the immune system and deploy that immune system that had been inactivated by cancer against the cancer itself. This idea has come out of really decades-long work, but reinforces the metaphor that the disease is inside the body and potentially the cure is also inside the body. This is the pivotal trial, data from the pivotal trial that showed the effectiveness of immunotherapy in lung cancer. And I had made a personal sort of theoretical bet that during my lifetime we would not see a therapy that would be successful for lung cancer. And I was wrong. This, in fact, is a successful therapy for admittedly a smallish fraction of patients with lung cancer, but certainly an effective therapy for lung cancer and melanoma being the first two. I therefore want to return to the questions that I had asked in the beginning of the talk, which the questions remembering Laurie Wilson's welcoming into this world, remembering the fact that now that welcome is rapidly expanding its horizons. We have two mechanisms that we are using to double, triple, quadruple the entry of people without cancer into Cancerland. We think, and there is powerful evidence to believe, that some of these people actually will have therapeutic benefit from the various therapies that we're inventing concomitantly as these patients enter Cancerland. But of course, the idea of being under surveillance and resurveillance, the idea of being described as a person at risk and being described as a previvor of cancer itself has caused already fundamental changes in how we imagine ourselves, fundamental changes in how we imagine our vulnerabilities, and fundamental changes in what the institution of cancer represents for human beings. And of course, this is why I was reminded of work by Goffman, and all of a sudden began to understand, sitting in my clinic in New York City, began to understand how much of the totality, how much of danger we have in inventing and deploying the totality of institution of cancer for individuals who are actually cancer-free or maybe just prone to cancer because of genetic risk. So I'll end again with repeating the concerns about a culture where we are expanding or dilating the totality of institution of cancer, and wonder with you whether this is a cultural risk or a behavioral risk that's worth taking. Would we want to live in a society where our own bodies are under surveillance, even if it's for therapeutic benefit? Would you want to inhabit that place? Are we ready to open this experiment of using powerful therapies, potentially curative therapies, in men and women who have the earliest signs of cancer. What would we do? How would we run that experiment? And finally, what it does to the idea of does it similarly situate us, to use Erving Goffman's word, cut off from a wider community of those who are not previvors for a considerable time, forced then to lead an enclosed, formally surveyed, administered round of life. And once again, therefore, remembering Stephen Shapin's idea that came back to me really almost a decade after he had reviewed reviewed my book. And I'll read that to end now with a renewed understanding, I hope, of what it might be to live in this culture of surveillance where the body is perpetually a site or a locus of future cancer. A world in which cancer is normalized as a manageable chronic condition would be a wonderful thing, but a risk factor world in which we all think of ourselves as precancerous would not, Shapin argues. It might decrease the incidence of some forms of malignancy while hugely increasing the numbers of healthy people under medical treatment. The question is open whether it would be a strange victory in which the price to be paid for checking the spread of cancer through the body is its uncontrolled spread through the culture. Thank you very much. I'll be delighted to answer any questions. Yes. There are a couple, yeah, on these two corners. There's a mic coming towards you. I'm going to have a sip of my tea.
Thank you so much. This is wonderful and terrifying at the same time. You showed a slide in which you were talking about blood testing of various types of cancer and that there was 100% accuracy after the fact with ovarian cancer. Is there a simultaneous testing of well people so that you can get a sense of what the percentage is of well people who also have those trace
elements? So that is the entire point of the test. The entire point of the test is to deploy them on people who are well, so that these cancers, which are particularly the ones that are occult, ovarian, pancreas, and others, would be detected before they could be detected visibly by any other means. This, as I said, is the dilation of the world of cancer. The purpose of this test the ultimate purpose of this test is not to diagnose women who've already been diagnosed with cancer or men who've already been diagnosed with cancer, but to find those women and men whose cancer has not been diagnosed and ask the question, can you diagnose them before it's visible by any other means?
No, I understood that. I meant well people who remain well.
Yes, absolutely. So this is, in other words, in the fantasy of this test, it would be well people who remain well and would be continuously surveyed, if that's what you're asking, until they presumably began to develop signs of one of the various cancers. They would be continuously surveyed. By the way, I understand why it's terrifying. You also must understand how exhilarating it would be to detect an ovarian cancer before it spread. How exhilarating it would be to detect a melanoma before it became metastatic. I mean, this is what we had dreamed about in the world of cancer and cancer prevention. This was the dream. It's just that when the dream is coming closer and closer, it seems that we are not very comfortable with important aspects of it. But let me not minimize how exhilarating it would be. Yes, sorry.
Hi, thank you for the talk. I'm trying to figure out which side of it you come down on, because you raised the prospect of us all being in this pre-Viva world, but at the same time, you seem very enthusiastic about some of the studies that are being done in their ability to predict. And secondly, is there any doubt that we would all get progressively more comfortable with the idea of being in this pre-Viva world? I mean, after all, we get used to things like statins and many other preventive medicines. So is there any doubt of where we are all eventually going to end up?
Well, I have doubts. I'm conflicted about it. I have doubts. I have doubts perceiving myself as a pre-Viver. I think it changes I think it fundamentally changes at a humanistic level. This is a this is a humanities lecture, and this is why I chose this topic. It fundamentally changes my imagination conception of myself. It fundamentally changes my imagination conception of those around me, my friends, my family, because I'm now thinking about themselves not only as in their sovereignty, but I'm thinking of them as loci of risk. I think it would be impossible to argue that that does not change who we are. We can certainly get comfortable with it, but with that comfort comes a fundamental change in who we think of ourselves as human beings. So I'm conflicted. Going back to your first question, I'm very conflicted about it. As I said, I'm an oncologist. I treat cancer. I write about cancer. I think about cancer all the time. And I understand, as I said to the first person who asked the question, let me not minimize the exhilaration of being able to detect a metastatic melanoma before it metastasized. But on the other hand, I do have conflicts about entering pre-viral world.
I know there's more questions, but I'm mindful of time.
Maybe we'll do one more so that then we can.
One more. Okay.
Yes, sorry, because they're now coming out of the woodworks.
Hi, yeah, I have a question about other diseases. So I think you talk about cancer, but it seems like there's a lot of diseases for which pre-vivorship might become an increasing reality. If cancer is unique, what sets it apart? And if it isn't, what do you think will become like cancer in that there are massive numbers of pre-vivors?
First of all, I don't think cancer is unique. It's only unique because it's such a powerful genetic disease. The genetics is so powerful. Last night, we actually had a very important conversation around the table around Alzheimer's disease or other neurodegenerative diseases where you can actually get risks based on genetics. You can get risks that may be 5, 7, 10-fold higher than the rest. So genetic diseases, and in fact, possibly diseases where you can see environmental stamps in chemical stamps of the environment on human cells, both would be amenable to this kind of surveillance. And in fact, as many of you know, this is already happening in diseases like Alzheimer's disease, cardiovascular disease, obesity, and of course going into a whole host of other things that we don't classify as diseases, but lie in the continuum of normalcy and normal traits. But going back to your question, could be reclassified as pathology once we start to think about them in quantitative ways. There's a fundamental danger there too, because once we begin to think of human variation in these quantitative ways as risk, the word risk itself implies pathology. So certainly other diseases, other traits, if hereditary, particularly if hereditary, are amenable to this kind of analysis. Thank you very, very much. Thank you.